Right now, something might be passing through your body. Not radiation, not gravity exactly. Something that has no name yet in any textbook. Something that interacts so selectively with matter that your atoms feel absolutely nothing. No warmth, no pressure, no signal of any kind. And the only reason physicists even suspect it exists is because a particle the size of nothing wobbled a fraction too much inside a magnetic ring in Illinois. That one tiny wobble may be the first fingerprint of a force connecting our visible world to a hidden sector, making up most of the cosmos. Get comfortable, subscribe if you're new, and stick around, because this story gets stranger the closer you follow it. Part 1. The claim that shouldn't be possible. There is a version of this story where everything is fine, where physics did exactly what it was supposed to do, where the machines worked perfectly, where the numbers came back clean, and where the greatest framework in the history of science held its ground without flinching. That version of the story is simpler. It is also not the version we are going to tell, because something happened, something quiet, something measured, something that emerged not from a dramatic explosion in a laboratory or a sudden catastrophic failure of equipment, but from a number in roughly the 8th decimal place, a number so small, so buried in the machinery of calculation, that you would need a lifetime of physics training just to understand why anyone should care about it. And yet, the people who did understand it, the people who had spent their careers constructing the most precise predictive framework in the history of human knowledge, they cared enormously, because in their world a deviation that's small is not a rounding error, it is a rupture. Let us take a step back for a moment, because the full weight of what we are about to discuss only lands if you understand what was at stake before the anomalies appeared. The standard model of particle physics is, in the most honest and literal sense of the phrase, one of the greatest intellectual achievements in human history. It is a mathematical framework that describes everything that matter is made of and every force that governs how matter behaves, with the exception of gravity, and it does so with a precision that has no parallel in any other branch of science. We're talking about predictions that match experimental results to 10 or 11 decimal places. Not roughly, not approximately, 10 decimal places. That is the equivalent of measuring the distance from New York to Los Angeles, roughly 2,800 miles, and being accurate to within the thickness of a single human hair. That is what the standard model does. That is what physicists had built, and then the numbers stopped cooperating. To understand why this feels so strange, you have to understand the history of the field. Physics is not a discipline where anomalies are taken casually. When something does not match the prediction, physicists do not shrug and move on. They check the calculation, they check the equipment, they check for sources of interference, they run the analysis again, and again, and then they hand it to a completely separate team of people and ask them to find the error. This process takes years, sometimes decades. The culture of particle physics was forged in the era when announcing a false discovery was considered one of the worst professional failures a scientist could experience. The standards for claiming a genuine discovery are extraordinarily high. A result needs to be something called 5 sigma, meaning the chance that the result is a random fluctuation rather than a real effect is less than 1 in 3.5 million, before the community will even begin to accept it as real. That is not caution. That is near paranoia. And it is earned because the history of the field contains numerous moments where something that looked like new physics turned out to be a systematic error nobody had thought to account for. So when physicists at Fermilab in Illinois and separately at CERN in Geneva began to see measurements that did not quite line up with what the standard model predicted, they did not celebrate. They did not call press conferences. They sat down and started looking for their own mistakes. What makes the story compelling? What makes it worth 16,000 words of careful exploration is that they kept looking, and the discrepancies kept surviving. Not conclusively, not unambiguously, but persistently in a way that began to feel less like noise and more like a whisper. Here is the central question that this entire story will orbit, and I want you to hold it in your mind from the very beginning. Could there be a force, a genuine, fundamental force of nature, that passes through ordinary matter so completely, so selectively, that it is physically impossible for us to detect it directly? Not difficult to detect, not requiring better technology, physically, impossible, because of what we are made of, because of the rules that govern how we interact with the world. What would that even mean for our understanding of reality? And if such a force exists, how would we ever know whether we had actually found it, or whether we were simply staring at noise and willing it into a pattern, the way humans have always done when confronted with something they desperately want to be true? This is not a story about a confirmed discovery. I want to be honest with you about that from the beginning, because the actual story is stranger and more interesting than a simple announcement would be. This is a story about a signal that appeared, that grew, that attracted enormous scientific attention, that began to be interpreted as evidence of something genuinely revolutionary, and that then began to flicker, to weaken, to resist the certainty that everyone wanted to assign to it. The anomalies we're going to discuss: a muon wobbling a fraction too much in a magnetic ring in Illinois, and a heavy quark in CERN's collider decaying in ways that seem to betray a subtle preference the universe was not supposed to have. These anomalies were not random noise from a poorly calibrated instrument. They came from two of the most carefully constructed, most rigorously analysed experiments in the history of science. They were taken seriously by serious people, and for a period of several years, they generated genuine excitement that the standard model might finally be showing its first real cracks that could be pointing toward an entirely new sector of reality, a hidden domain of particles and forces that we have never been able to see, not because our instruments are too weak, but because we are fundamentally tuned to a different frequency of existence. The possibility behind all of this, the thing that keeps physicists awake and keeps science writers reaching for their keyboards, is this. Most of the universe, the overwhelming majority of everything that exists, is made of stuff we cannot see, cannot touch, cannot detect with any instrument we have ever built. We call it dark matter. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force that governs virtually everything we experience. And for decades, the assumption has been that dark matter only interacts with ordinary matter through gravity, which is why we know it exists at all, because galaxies are moving in ways that only make sense if there is far more mass present than we can account for with everything we can observe. But what if gravity is not the only connection? What if there is a force, a fifth fundamental force, that bridges the visible and the invisible, that reaches across the divide between what we are made of and what most of the cosmos is made of? And what if the first faint trace of that force is precisely what appeared in those experiments, in those anomalies, in that whisper from the 8th decimal place? The physicists who study this say things carefully. They use phrases like intriguing hints and potential evidence, and requires further investigation. They are trained to resist the pull of premature certainty. But underneath the careful language there is something real, a sense that for a few years the universe briefly appeared to be telling us something, and then went quiet again, and the question of whether it was speaking, or whether we imagined it, is still open. That is the story. The deeper you follow the data, the stranger it gets, because the closer you look, the more you see that the line between discovery and illusion is not always where you expect to find it. And the most unsettling possibility, the one this entire investigation keeps circling back to, is that reality may be structured in such a way that certain truths are simply inaccessible to creatures built the way we are built. Not unknowable in principle, unknowable to us specifically, because of the physics of what we are. What if we already saw the signal? What if it was real, and we almost knew it? And then the data shifted and the certainty dissolved, and we were left with exactly what we started with. A feeling, a pattern, a number in the 8th decimal place that refused to be nothing but also refused to be proof. That question does not have a clean answer yet, but the journey toward it changes how you see everything. So let us begin. Part 2. The muon that refused to behave. The muon is, in many ways, a deeply inconvenient particle. It is not something you encounter in daily life. It does not make up the atoms in your body, or the molecules in the air or the light hitting your eyes as you read this. It is, in the most practical sense, unnecessary. It lives for roughly 2.2 microseconds, that is, 2.2 millionths of a second, before decaying into other particles and vanishing as completely as if it had never existed. It is 207 times heavier than the electron, which is its closest sibling in the family of particles we call leptons. And yet, for reasons that emerge from the deepest levels of quantum mechanics, the muon is almost uniquely suited to probing the fabric of reality at a level that no other particle can match quite as cleanly, which is exactly why, when the muon started behaving in a way that the standard model could not account for, people paid attention. The experiment at Fermilab in Batavia, Illinois is called the Muon G-2 experiment. The name comes from a quantity called the G factor, which is a number that describes how a particle responds to a magnetic field, specifically how its internal quantum spin aligns and precesses, or wobbles, in response to external magnetic forces. The G factor for an electron or a muon was predicted, even before quantum mechanics was fully developed, to be exactly 2. But then quantum field theory came along, and it introduced the concept of virtual particles, fleeting, ghost-like fluctuations in the quantum vacuum that pop in and out of existence in timescales so brief they border on the philosophical. And those virtual particles, it turns out, interact with the muon and subtly shift its G factor away from exactly 2. The difference between the actual G factor and 2 divided by 2 is called the anomalous magnetic moment, and it is labelled simply A sub mu, and calculating it precisely requires accounting for every single virtual particle, every quark, every boson, every fleeting quantum fluctuation, that the muon might interact with during its brief existence. The standard model can make this calculation. In fact, it makes it extraordinarily well. The predicted value and the measured value should agree to better than 1 part in a million. The fact that they agree at all at that level is genuinely remarkable. It is the kind of agreement that should make you stop and appreciate what theoretical physics has accomplished. But the Fermilab experiment was not looking for rough agreement. It was looking for the difference between extraordinary agreement and perfect agreement. And that difference, if it exists, is where new physics lives. The experimental setup at Fermilab is worth describing because it is, in its own way, a work of engineering art. The centerpiece of the experiment is a superconducting magnetic ring, a circular electromagnet with a diameter of roughly 50 feet, cooled to a temperature near absolute zero, generating a magnetic field so uniform and so precisely calibrated that the scientists describe it as the most uniform magnetic field ever produced by human hands. Muons are created by firing protons into a target, selecting only the muons that are spinning in the right direction, and then injecting those muons into the ring, where they begin to orbit the circular track while the magnetic field causes their spin to precess. That precession, that wobble, is what the experiment measures. Thousands of detectors arranged around the ring capture the signal of the decaying muons, and from the pattern of those decays, the physicists can extract the precession frequency with extraordinary precision. Think of it like watching a spinning top on a table. If you tilt the table slightly, the top will begin to wobble around its own axis in a predictable way, and the rate of that wobble depends on the properties of the top, its weight, its spin, its moment of inertia. Now imagine that the top is a muon, the magnetic field is the tilted table, and the wobble is the anomalous precession you are trying to measure. The difference from the predicted rate of wobble is the anomalous magnetic moment, and if it wobbles slightly faster or slightly slower than theory predicts, something is interacting with it that the theory did not account for. The experiment ran at Brookhaven National Laboratory in New York for years in the early 2000s, and already there it showed a discrepancy, a measurement that was slightly higher than what the standard model predicted. The result was tantalizing but not conclusive. The uncertainty in the measurement was large enough that the discrepancy could have been a statistical fluctuation. The equipment was then painstakingly moved to Fermilab, and when I say moved, I mean the 50-foot magnetic ring was physically transported on a flatbed truck across 900 miles of highway, with traffic held back along the route, because the ring was too delicate to disassemble and reassemble without risking damage to its extraordinary precision. That move alone took 15 months of planning and a nighttime convoy that briefly became its own news story. The Fermilab run began accumulating data in 2017, and in April of 2021, the first results from Fermilab were announced. The measurement confirmed and extended the discrepancy from Brookhaven. The combined results showed a difference between the measured value and the standard model prediction of about 2.4 parts per million. That sounds almost nothing. It is almost nothing. But in the world of precision physics, where the standard model's predictions are supposed to be accurate to 1 part per million or better, a discrepancy of 2.4 parts per million is a very large number. The statistical significance of the combined result was 4.2 sigma, close to the 5 sigma threshold for discovery, but not quite there. Close enough to be taken seriously. Close enough to generate enormous excitement in the physics community. And close enough to the discovery threshold that every subsequent measurement would feel like a verdict approaching. What made the anomaly especially interesting was not just its size, but its nature. If the muon is wobbling faster than it should, something is interacting with it, something that the standard model does not include. Virtual particles from known physics contribute to the wobble in precisely calculated ways. An additional contribution from an unknown particle, some new boson, some carrier of a fifth force, would push the wobble in exactly the direction the experiment was seeing. You cannot identify that unknown particle directly from this measurement alone. The muon does not leave a note explaining which ghost touched it. But you can infer that something is there, something the standard model has not accounted for, something that interacts with muons in a way that nudges their spin just a fraction, beyond what theory expects. And then, as we will see much later in this story, something happened to complicate the picture. The theory shifted. Not the experiment, the calculation. The universe didn't change, but our map of it did. The muon's misbehavior in the end was not a loud crash. It was a gentle drift, a quiet departure from the expected path, measured over years of patient observation in a magnetic ring the size of a small house. The universe did not announce itself. It just wobbled slightly in the 8th decimal place and waited to see if anyone was paying close enough attention to notice. Someone was, and that attention is about to get us into even stranger territory. Part 3. The Universe. Playing favourites. While the muon was misbehaving in a magnetic ring in Illinois, something equally unsettling was happening 4,000 miles away, under the mountains near Geneva, Switzerland. And the reason this matters, the reason it needs to follow directly from the muon story rather than stand on its own, is that 2 completely independent anomalies, emerging from 2 completely different experiments, studying 2 completely different kinds of particles, both pointing in the same direction, is not something you can easily dismiss as coincidence. The Large Hadron Collider Beauty Experiment, LHCb for short, was designed for a specific and somewhat specialized purpose. While other detectors at CERN are built to find new particles by smashing protons together at the highest possible energies and watching what flies out, LHCb is built to study the behavior of particles called B-mesons, particles that contain what physicists call a beauty quark, or sometimes a bottom quark. These are heavy, unstable particles that live for roughly 1.5 trillionths of a second before decaying into lighter particles. The reason for studying them is that the way they decay can be extraordinarily sensitive to physics beyond the standard model. Tiny, barely detectable influences from unknown particles or forces can shift the decay rates in measurable ways. It is essentially a different strategy for finding new physics. Instead of looking for new particles directly, you watch known particles decay and look for any signs that something unknown is influencing the process. The standard model makes a specific and very clean prediction about how B-mesons decay. One of the most important predictions involves something called Lepton universality. Leptons are particles like electrons and muons, light particles that do not feel the strong nuclear force. The standard model insists with a high degree of confidence that the laws governing the interaction of the weak nuclear force with leptons should be completely identical for electrons and muons, after you account for the difference in their masses. This is called Lepton universality, and it is not just an assumption. It is a consequence of deep mathematical symmetries in the theory. If you produce a B-meson and let it decay, the probability that it will produce an electron versus the probability that it will produce a muon should be, after mass corrections, exactly equal. The universe, in the standard model, does not play favourites between these 2 particles. LHCb watched B-mesons decay, and the decays were not equal. The ratio of decays producing muons to decays producing electrons was consistently lower than the standard model predicted. Not dramatically lower, not in a way that a casual observer would notice, but with a statistical significance that grew as more data was collected, and that reached levels that made physicists sit up and take the result very seriously. In some channels, the discrepancy was roughly 15%. 15% sounds small, but in a theory that predicts exact equality and has been confirmed in countless other measurements, 15% is a canyon. It means that B mesons were, by some unknown mechanism, less likely to decay into muons than they were supposed to be, or, equivalently, more likely to decay into electrons than expected. Either way, something was tilting the odds. Think of it this way. Imagine you have a perfectly fair coin, and you flip it 1,000 times, and you get 425 heads. That is unusual, but it might be bad luck. Now flip it 10,000 times, and you get 4,250 heads. Now flip it 100,000 times, and the ratio stays stable at 42.5% instead of 50%. At some point, you stop saying bad luck and start saying the coin is biased. That is roughly what was happening with the B meson decays. The universe was behaving as if it had a preference, as if it found muons slightly less interesting than electrons, as if something was quietly discouraging the decay path that produced the heavier lepton. What could cause this? The standard model has no mechanism for it. Lepton universality is not a suggestion in the standard model. It is a fundamental symmetry. If it is violated, something is interacting with these particles that is not in the theory. And the candidates that theorists began proposing were precisely the same kinds of objects that could also explain the muon's anomalous magnetic moment. New heavy particles, possible carriers of a fifth force, that interact preferentially with muons over electrons. Some proposals invoked a new boson, a Z-prime, a hypothetical particle similar to the Z boson that carries the weak force but with different interaction rules. Others proposed leptoquarks, exotic particles that can interact with both quarks and leptons simultaneously, and could therefore influence the B meson decays in exactly the way LHCb was seeing. The critical point, and this is where the story becomes genuinely strange, is that these two anomalies were completely independent. The Muon G-2 experiment at Fermilab was measuring a completely different quantity, using a completely different technique, at a completely different facility, and the result was not in any way connected to the LHCb measurement, except in this one detail. Both anomalies involved muons specifically. The muon was the common thread, and in physics, when two independent measurements that have nothing to do with each other both point at the same particle, that is when the community starts to take the pattern seriously. That is when coincidence starts to feel like a description that requires justification. The idea that was beginning to form in the minds of theorists was this. What if there is a force that selectively interacts with muons? Not a force that affects all matter equally, the way gravity does, or all charged particles equally, the way electromagnetism does, but a force that is peculiarly, specifically attentive to one particular kind of particle. A force that nudges the muon's spin in a magnetic field and simultaneously discourages certain decay processes involving muons. A force that, for reasons rooted in its own deep structure, simply does not care about electrons or quarks or protons or anything else that ordinary matter is made of. The universe, for a few years, appeared to be playing favourites, and then, but we will get to that, the pattern needs to be built before it can begin to dissolve. Part 4. Naming the invisible. At some point in science, you reach a threshold where the evidence is not sufficient to confirm a theory, but is sufficient to justify naming it. That threshold had been crossed. Physicists began writing papers, hundreds of them, attempting to identify what kind of new physics could simultaneously explain the Muon anomalous magnetic moment and the lepton universality violation in B meson decays. And the most commonly invoked candidate had a name, a fifth fundamental force. To understand what that means, you need to briefly understand how forces work in the quantum mechanical picture of reality. We experience forces as pushes and pulls, gravity pulling you toward the Earth, magnetism attracting or repelling a compass needle, the nuclear forces holding atoms together. But in the language of quantum field theory, forces are not transmitted by direct contact or by action at a distance. They are transmitted by particles, specifically by particles called bosons, which are the carriers of force. The electromagnetic force is carried by photons, yes, the same particles that make up light. The weak nuclear force is carried by the W and Z bosons. The strong nuclear force, which binds quarks together inside protons and neutrons, is carried by particles called gluons. every force has its carrier, and if there is a fifth force, it must have a carrier too. The most widely discussed candidate for the carrier of a muon-specific fifth force is something theorists call the Z-prime boson. The name is deliberately evocative of the Z boson, the carrier of the weak force, because the Z-prime would play a similar structural role, mediating an interaction between particles. But unlike the Z boson, which couples to all fermions more or less equally, the Z-prime would have strongly preferential couplings. It would interact vigorously with muons and perhaps with whatever particles constitute dark matter. It would interact barely at all, or not at all, with electrons or with the quarks that make up protons and neutrons. This selectivity is not physically impossible. There is no fundamental reason why every force must treat every particle equally. The forces we already know do not in fact treat all particles equally. The strong force only affects quarks and gluons, not electrons. The selectivity itself is not what makes the Z-prime exotic. What makes it exotic is that it would be selective in a way that corresponds exactly to the anomalies we're seeing, and that it has not shown up directly in any particle detector, which means it must be heavy enough and weakly enough coupled that it has so far evaded detection. Another popular candidate is the leptoquark, a hypothetical particle that does something particles in the standard model do not do. It simultaneously carries both lepton number and baryon number, which means it can interact with both leptons and quarks in a single vertex. This sounds abstract, but the consequence is concrete. A leptoquark could mediate the specific B-meson decay that LHCb was studying, converting a bottom quark into a strange quark, while also converting a lepton from one type to another, or influencing the ratio of muons to electrons in the final state. Leptoquarks appear in various theories that extend the standard model, including some grand unified theories, and they have been searched for at CERN without success, which means that if they exist, they are either very heavy, or they couple very weakly to the particles we have been looking at. What both of these candidates share, the Z-prime and the leptoquark, is a property that could be described, with only slight melodrama, as elitism. They would not democratically interact with all matter, they would pick and choose. And this selectivity, this preference for muons over electrons, is precisely what makes the anomalies so tantalizing, and what makes the fifth force hypothesis genuinely different from simply adding another particle to the standard model. It suggests a force that is structured around a different set of rules, a different layer of interaction, that ordinary matter is almost entirely immune to. Think about what that means for a moment. The forces you interact with every day, electromagnetic forces holding your cells together, keeping electrons bound to nuclei, allowing chemical reactions to happen, allowing light to carry information from the world to your eyes. These are forces you participate in because you're made of electrically charged particles. You have charge, you have mass, you have the quantum numbers required to interact. But the fifth force, in this picture, would require a different quantum property, one that ordinary matter possesses only barely or not at all. It would be like a radio station broadcasting on a frequency that your receiver is not built to tune into. The signal could be all around you, moving through you, propagating through the chair you're sitting in, and the walls of the room, and the core of the planet beneath your feet, and you would feel absolutely nothing. Not a vibration, not a warmth, not a whisper, nothing. And here is where the story takes its first turn toward the genuinely existential. Because the fifth force hypothesis is not just about two anomalies in particle detectors, it is about what those anomalies might be connected to. If a force exists that interacts selectively with muons and ignores ordinary matter, then what else does it interact with? What if the very reason it ignores ordinary matter is that it is primarily designed, if we can use that word loosely, to interact with something else? Something we cannot see, something that, in terms of sheer quantity, vastly outnumbers everything we have ever observed. The answer that theorists kept reaching for, the answer that gave the fifth force hypothesis its most alarming implications, was dark matter. And to understand why that connection matters so much, we have to talk about the scale of what we do not know. Part 5. The Cosmic Radio. Here is an image I want you to sit with for a moment. Imagine that the entire electromagnetic spectrum, from radio waves longer than a football field to gamma rays with wavelengths smaller than an atomic nucleus, represents all the ways that reality can communicate with itself, all the channels, all the frequencies, and imagine that we, as beings built from atoms and governed by the foreknown forces, attuned to a very small portion of that spectrum. We can see visible light. We can build instruments to detect radio waves, X-rays, infrared radiation. We can, in principle, detect gravitational waves, ripples in space-time itself. Our instruments have extended our natural perceptions enormously, but we are still fundamentally constrained by the forces that govern us. We can only detect what interacts with us. We can only hear the channels we are built to receive. Now imagine, just as a thought experiment for now, that there are other channels, not electromagnetic channels, because that spectrum is already fully mapped, but force channels, interaction channels, channels that operate through quantum properties we do not possess, particles travelling through a room, information being transmitted across cosmological distances, structures forming and dissolving, all through a mechanism that requires a different kind of charge to access. And we, built entirely from the particles that interact with four specific forces, sit inside this transmission completely unaware, the way a radio receiver tuned to AM frequencies sits in a room filled with FM transmissions and hears only silence. This is not science fiction. This is a serious way of thinking about what the fifth force hypothesis could actually mean if it is correct. The reason we cannot detect certain things is not always that our instruments are too weak. Sometimes it is that our instruments are built from the wrong materials. Sometimes it is that the thing we are trying to detect interacts with a quantum property that none of our instruments possess, because none of our instruments are made of the right stuff. This is not a technological limitation. It is a structural one. And that distinction matters enormously when we are trying to assess the fifth force anomalies, because it raises a question that is simultaneously scientific and philosophical. How do you distinguish between a signal you cannot detect and a signal that does not exist? The Muon anomaly and the Lepton universality violation at LHCb become interesting again in this context. Because here is what makes the muon special in this framework. The muon is not ordinary matter in the same way a proton or an electron is. It is fleeting, exotic, produced only in high-energy collisions. But it is also a particle that interacts differently from electrons in subtle ways that we do not yet fully understand. And if a fifth force exists that couples to muons but not to electrons, then the muon is not just a heavier cousin of the electron, it is a partial bridge, a particle that belongs mostly to our world but has one foot in another channel, a particle that can briefly hear a transmission that the rest of ordinary matter is deaf to. This is why both anomalies involve the muon specifically. This is why the pattern made theorists excited. Not just because two experiments agreed, but because the agreement pointed at the muon as a uniquely privileged observer, a particle that was in some sense tuned to both frequencies at once. The troubling flip side of this picture is one you should sit with rather than dismiss. If the fifth force couples so weakly to ordinary matter that we can only see it through the indirect effects it has on muons, then we are by definition in a very difficult position when it comes to confirmation. Every piece of evidence we can gather will be indirect. Every measurement will involve detecting the echo of an interaction rather than the interaction itself, and echoes, in physics as in life, can be misinterpreted. The room you think you're hearing can be different from the room that actually produced the sound. Is what we found a genuine signal from another frequency of reality? Or have we been sitting in a very quiet room, hearing our own blood pressure and calling it music? That question, as uncomfortable as it is the central question of this entire story. And to understand just how high the stakes are, just how much depends on the answer, we need to understand what the signal might be telling us about the hidden majority of everything that exists. Part 6. The Dark Majority. There is a number in cosmology that should bother you more than it does. The ordinary matter, the protons, neutrons, electrons and photons that make up everything you have ever seen, touched, measured or built instruments to detect, accounts for roughly 5% of the total energy content of the universe. 5%. Everything. Every star, every planet, every atom, every galaxy, every human, everything that has ever interacted with any instrument we have ever built. 5%. The remaining 95% of the universe is composed of things we cannot directly detect. Roughly 27% is dark matter. Matter that has mass and therefore gravity, but does not interact with the electromagnetic force and therefore cannot emit, absorb or reflect light. The remaining 68% is dark energy, an even more poorly understood phenomenon driving the accelerated expansion of space itself. Today, we're going to focus on the dark matter, because it is the part of the missing majority that connects most directly to the fifth force anomalies. We know dark matter exists for several reasons, but the most intuitive is also the oldest: the rotation of galaxies. When astronomers measure how fast the stars at the outer edges of a spiral galaxy are orbiting around the galaxy's centre, they find speeds that are far too high. In a normal distribution of mass, concentrated at the centre like we observe with visible stars and gas, the outer regions should orbit more slowly, the way the outer planets of our solar system orbit the Sun more slowly than the inner ones. This is simple Newtonian gravity. But the outer edges of galaxies do not slow down. They orbit at nearly the same speed as the inner regions. The only explanation that works is that there is a massive, invisible halo of matter surrounding and extending beyond the visible galaxy. Matter that contributes gravitational pull without contributing any detectable light. And the amount of this missing mass is not small. It is, on average, about 5 to 6 times the mass of all the visible matter in the galaxy combined. So we have established that dark matter is real, that there is vastly more of it than visible matter, and that it has mass. What we do not know is what it is made of, and crucially, what we do not know is whether it interacts with ordinary matter through anything other than gravity. For decades, the default assumption was that it does not, that dark matter is inert, gravitationally active but otherwise completely isolated from the forces that govern our world. Numerous experiments have been built deep underground to try to detect dark matter particles directly. Tanks of xenon, arrays of germanium crystals, spheres of liquid argon, and none of them have found anything conclusive. Dark matter, whatever it is, has been extraordinarily good at hiding. Now we arrive at the connection that makes the fifth force hypothesis something more than just a curiosity about a couple of particle physics measurements. If a fifth force exists, one that couples to muons, one that ignores ordinary electrons and quarks, one that is carried by a new boson that we have not yet directly detected, then the question naturally arises, what else does this force couple to? And the theoretically clean answer, the answer that appears in many of the models proposed to explain the anomalies, is dark matter. The Z-prime boson, or the leptoquark, or whatever carrier particle mediates this hypothetical fifth force, could in principle interact with both the muon sector of visible matter and with the hidden sector of dark matter simultaneously. It would be a bridge. Not a gravitational bridge, gravity already connects everything, but an actual force bridge, a channel of non-gravitational interaction between the visible 5% and the invisible 27%. This is why the anomalies, if real, matter far beyond the immediate world of particle physics. Because if the fifth force is the bridge to dark matter, then the faint statistical deviations in a magnetic ring in Illinois and a detector at CERN might be the first time in human history that we detected something from the dark sector through a mechanism other than gravity. The first time the dark majority reached across the divide and tapped ordinary matter on the shoulder. And we almost noticed. The central question here, is this signal real or illusion, becomes sharper when you understand the stakes. If real, we have not just found a new particle, we have found a crack in the wall between the observable universe and the invisible majority that constitutes most of what exists. That is not a small result. That is, arguably, the most important discovery in the history of physics. Which is exactly why the subsequent complications in the data are so important to understand honestly rather than to ignore. Part 7. Seeing the invisible. Let me be clear about what this section is. It is informed speculation. Theoretical physics is full of ideas that have not yet been confirmed, that may never be confirmed, but that follow logically from things we already believe. And some of those ideas, when you lay them out carefully, reveal something about the potential scope of what we might be missing. So let me walk you through a few of them, with the clear understanding that we are now in the territory of theory rather than measurement. If a fifth force exists that mediates interactions between the muon sector of visible matter and dark matter, it is natural to ask whether dark matter itself could form complex structures analogous to what visible matter forms. The standard picture of dark matter treats it as a collection of essentially featureless particles, point masses that clump together under gravity and nothing else. But if dark matter has its own force, its own version of electromagnetism mediated by something theorists call a dark photon, then dark matter could in principle interact with itself. It could form dark atoms, dark molecules. It could emit and absorb dark light, radiation that is completely invisible to us because it interacts only with dark charge, not with ordinary electric charge. It could, in a genuinely staggering possibility, form dark stars, objects in which dark matter clumps together, heats up under gravitational pressure, and begins to radiate dark light that we cannot see. There is no observational evidence for any of this. None of these structures have been detected because, by definition, if they emit only dark light, no instrument built from ordinary matter will register them. But whether these ideas are right or wrong connects directly back to our central question, because the answer depends on whether the anomalies at Fermilab and CERN are real. If they are real, if the fifth force exists and couples both to muons and to dark matter, then the dark sector is not just a cloud of gravitationally active dust. It is a world, invisible, inaccessible, but real, filled with its own physics, its own chemistry, its own structures, passing through us constantly, overlapping with our space, sharing our gravity, and utterly beyond our reach. If the anomalies are noise, if the measurements turn out to be statistical fluctuations or theoretical errors, then this entire picture collapses back into speculation with no anchor in observation. That is the pivot point. Everything in this section rests on a signal that has not yet been confirmed, and that is exactly why the next part of the story, the engineering, the scale, the machinery we built to try to resolve the question, matters so much. Part 8. Why we had to break reality to look. There is a building 27 kilometers in circumference buried under the French and Swiss countryside near Geneva. To put that in terms, you can feel, if you got in a car and drove at highway speed along the tunnel that houses this machine, it would take you roughly 16 minutes just to complete one lap. The tunnel itself sits between 50 and 175 meters underground, carved through rock and clay and ancient seabed that was at the bottom of a shallow ocean tens of millions of years ago. $10 billion and a decade of construction. Thousands of engineers, physicists and technicians from over 100 countries contributing to a single machine. And when it was finished, it did not look like much from the surface. A few unremarkable buildings scattered across fields on the outskirts of Geneva, connected by access shafts to something extraordinary happening far beneath your feet. The Large Hadron Collider is cooled to a temperature of 1.9 Kelvin. That is 1.9 degrees above absolute zero, the theoretical temperature at which all molecular motion stops entirely. To give you a reference point, the average temperature of empty space far from any star, warmed slightly by the leftover radiation from the Big Bang, is about 2.7 Kelvin. The LHC is colder than the universe's background temperature. It is colder than the surface of Pluto, which sits at around 44 Kelvin. It is colder than almost any naturally occurring environment in the observable cosmos. Achieving and maintaining that temperature requires roughly 10,000 tons of liquid nitrogen for pre-cooling, and over 120 tons of superfluid liquid helium distributed through a plumbing system that stretches the full circumference of the ring. This is not incidental engineering. The extreme cold is essential because the superconducting magnets that steer the protons only become superconducting, meaning they carry electrical current with zero resistance, at temperatures this close to absolute zero. Warm them by even a fraction of a degree in the wrong place, and they quench, losing superconductivity instantly, releasing their stored energy in a violent pulse that can damage the surrounding equipment. The LHC has quenched before. It is not a pleasant event. Inside this frozen ring, protons are accelerated through a sequence of smaller machines before being injected into the main collider, where they travel in two beams moving in opposite directions, reaching speeds of 99.999999% of the speed of light. At that speed, relativistic effects become significant in ways that matter for the engineering. The protons experience time differently from the engineers monitoring them on the surface. Their effective mass, from the perspective of the laboratory frame, increases enormously. This is the energy that makes the collisions useful. The magnets that guide them must generate fields roughly 100,000 times stronger than the Earth's magnetic field to keep the beams on their circular path rather than flying off in straight lines. There are about 9,600 superconducting magnets of various types arranged around the ring, dipole magnets for bending, quadrupole magnets for focusing, higher order magnets for fine corrections, each one a precision instrument, each one individually tested, each one cooled to that extraordinary temperature and maintained there continuously during operation. When the two beams are brought together at the collision points, the energy released is, by everyday human standards, almost nothing. Each collision releases roughly the same kinetic energy as a flying mosquito, but that energy is concentrated into a space smaller than an atomic nucleus, a volume so tiny that the comparison to a mosquito becomes almost absurd. You're taking the energy of an insect in flight and compressing it into a space roughly 10 to the power of negative 15 meters across. At that concentration, the energy density reaches conditions that have not existed freely in the universe since approximately 1/trillionth of a second after the Big Bang. Particles that have been absent from the natural world for 13.8 billion years briefly flicker back into existence in the debris of that collision, live for a fraction of a second, and decay into other particles that the surrounding detectors record. That is the strategy. Recreate the early universe, locally, briefly, and watch what falls out. The LHCb detector, the one most relevant to the Muon anomalies, and the Lepton universality measurements we have been discussing, is a specialized instrument positioned at one of the collision points. Unlike the large general-purpose detectors like ATLAS and CMS, which surround the collision point in all directions like enormous spherical cameras, LHCb is a forward spectrometer, shaped more like a series of flat panels arranged along one side of the beamline. This design reflects its purpose. The beam-mesons produced in proton collisions tend to fly forward along the beam direction, and LHCb is optimized to catch them, track their trajectories, and reconstruct their decays with extraordinary precision. It can identify individual particle tracks to within a few tens of micrometers, about the width of a human hair, which is already almost insultingly inadequate as a comparison for how small we are actually talking about. For Run 3, which began in 2022, LHCb was essentially rebuilt from scratch. The entire trigger system, the electronic nervous system that decides, in real time, which collision events to keep and which to discard, was replaced with a completely software-based architecture. The new system processes approximately 1 terabyte of data per second. 1 terabyte, every second, continuously. The computing farm that handles this sits in a room the size of a modest warehouse, humming with the heat of thousands of processors all running simultaneously, evaluating every single proton collision as it happens, applying machine learning algorithms trained on millions of simulated events, deciding within microseconds whether each collision contains anything worth saving. Only events with the signatures of heavy quark decays, rare processes, or potential new physics make it through the filter. The rest, the overwhelming majority of the roughly 30 million collisions happening every second at the LHCb interaction point, are discarded in real time and are gone forever. The collision energy in Run 3 was increased from 13 tera-electron volts to 13.6 tera-electron volts. That 6% increase sounds modest. In practice, it meaningfully extends the range of particle masses the LHC can probe, pushing the boundary of what new physics could be directly produced if it exists. Higher collision energy means heavier particles can be created. If the Z-prime boson, or the leptoquark, the hypothetical carriers of the fifth force that would explain the Muon anomalies, sit just beyond the reach of Run 2 energies, Run 3 might be able to produce them. The higher luminosity, meaning more collisions per second, also means that rare processes, the kind of low-probability events that carry the most information about new physics, accumulate in the dataset faster. LHCb in Run 3 is expected to collect more data in a few years than it did in all of its previous operation combined. And yet, with all of this, with the most energetic proton collisions ever achieved on Earth, with detectors rebuilt to unprecedented sensitivity, with data processing capabilities that would have seemed like science fiction to the physicists who designed the original machine, we have still not directly detected the new particles that the fifth force hypothesis requires. No Z-prime boson has materialized in the collision debris. No leptoquark has been reconstructed from the particle tracks. The indirect hints that excited the community, the wobbling muon, the the skewed decay ratios. Those were there, in the statistics, in the careful comparisons between measurement and theory. But the direct evidence, the clean peak in a mass distribution, the unmistakable signature of a new particle decaying into known particles in a way that nothing in the standard model can produce, that has not appeared. The smoking gun remains absent. This puts us in an uncomfortable but honest position. There are two interpretations available, and neither is fully satisfying. The first is that the fifth force is real, that the new particles exist, but that they are either too heavy for the LHC to produce directly, or that they couple so weakly to the particles we are colliding that the production rate is simply too low to see in the current dataset. In this scenario, we are not wrong, we are just undershooting. The universe contains the answer we are looking for, and we need a bigger machine, or more time, or a different approach. The second interpretation is the one that requires more intellectual courage to sit with. The particles are absent because they do not exist. The anomalies were fluctuations. The fifth force is not there. The standard model, battered but unbroken, was right all along. The LHC was supposed to be the machine that resolved this. In the popular imagination, and to some extent in the professional one, it was the instrument that would force reality to reveal its hidden layers. And it has done that spectacularly in many ways. It found the Higgs boson. It has measured properties of known particles with extraordinary precision. It has excluded enormous regions of theoretical parameter space, ruling out hundreds of proposed extensions of the standard model with cold efficiency. What it has not done, at least not yet, is deliver the specific verdict this particular story demands. It has produced, instead, more precise versions of the question. The anomalies that survived Run 2 have been subjected to more data in Run 3, and the results continue to arrive, continue to be analysed, continue to resist the kind of clean resolution that would let anyone write a definitive final chapter. The most powerful machine ever built to probe the structure of reality has so far refused to tell us whether the whisper we heard was real. And that refusal, that suspended uncertainty, that moment before knowing that stretches across years of data collection and analysis, is perhaps the most honest thing the universe has said to us in a long time. It has not confirmed the force, it has not denied it, it has simply continued operating according to its own rules, indifferent to our need for clarity, while we sit at the edge of what we can measure and listen as carefully as we possibly can for something that may or may not be there. Part 9. The moment before. Knowing. Science has a number system for uncertainty, and it is worth explaining carefully because it governs everything about how the story of the fifth force anomalies is unfolded, and because without it, the headlines make no sense, and the actual situation makes even less. When physicists report a result, they attach to it a number called the sigma level. Sigma is a measure of statistical significance, and it describes, in a single number, how confident the researchers are that what they measured is a real effect rather than a random fluctuation of the data. 1 sigma means there is about a 32% chance the result is a fluke, which is to say nearly 1 in 3. That is terrible odds. You would not bet your career on 1 sigma. You would not even bet lunch on 1 sigma. 2 sigma means roughly 5%. Better, but still 1 in 20, still well within the range of results that vanish entirely when you collect more data. 3 sigma, which the field formally calls evidence, with deliberate caution built into the vocabulary itself, means there is about a 0.3% chance it is a fluke. That sounds small, and it is small. But particle physics has been burned by 3 sigma results, often enough that the community treats them as interesting leads rather than conclusions. 5 sigma is discovery. 5 sigma means the probability that the result is a random fluctuation is less than 1 in 3.5 million. To put that in terms you can feel, if you flipped a fair coin and needed it to land heads 22 times in a row to match the odds, 5 sigma is roughly that unlikely. It is not impossible. Genuinely unlikely things happen. But at 5 sigma, the physics community has decided, through hard experience, that the probability of being fooled by statistics is low enough to stake a claim. Below 5 sigma, you are in the territory of pursuing the result, not announcing it. These numbers are not arbitrary thresholds dreamed up by overly cautious committees. They emerged slowly and sometimes painfully from the history of the field itself. Particle physics in the latter half of the 20th century was littered with high-profile 3 sigma results that generated enormous excitement and then quietly dissolved when better data arrived. There were hints of particles that conferences were organized around, papers that were written, careers that were partially built on signals that turned out to be statistical accidents. Each of those episodes cost something: time, credibility, the misdirection of enormous resources, and the community responded collectively by raising its standards and codifying them. The 5 sigma rule is scar tissue. It is the field's institutional memory of how badly motivated human beings want to find new physics, and how easily that desire can distort what they see in a dataset. Understanding this is essential for understanding why the Muon G-2 result and the LHCb Lepton universality measurements generated the response they did. At their peaks, these anomalies were sitting at roughly 4 sigma and 3.1 sigma respectively. That placed them firmly in the zone of serious scientific attention, not dismissible, not confirmable, but requiring pursuit. The community knew from experience that 4 sigma results sometimes become 5 sigma discoveries with more data, and sometimes become 1 sigma fluctuations that nobody talks about anymore. The only way to find out which story you're living is to collect more data and see which direction the significance moves. One of the most remarkable aspects of how modern particle physics manages not just the statistics, but the psychology of its own investigations is a practice called blinded analysis. It is worth spending real time on this, because it reveals something important about how humans relate to evidence when they have strong expectations about what they want to find. When an experiment is preparing to release a new result, the data is deliberately obscured in a specific technical way. The teams analysing it cannot see the actual numerical value of the quantity they're measuring, whether the anomaly is large or small, present or absent, until after every element of their analysis has been decided and locked in. They choose, in advance and in writing, exactly how they will process the raw data, which events will be included in the sample, which systematic effects they will correct for and by how much, what their statistical method will be, how they will handle edge cases, what their final result will look like in terms of format and presentation. All of this is decided, documented, and frozen, and only then, after the entire analysis pipeline has been sealed against modification, is the blind lifted. The number appears, and whatever it is what the analysis produces, because there is no longer any way to adjust the analysis to push the number somewhere more convenient. This is not paranoia. I want to be precise about that, because it would be easy to read the practice of blinding as an admission that physicists are untrustworthy or prone to fraud. That is not what it is. The people working on these experiments are extraordinarily careful, deeply committed to getting the right answer, and professionally invested in finding the truth rather than confirming a preferred result. Blinding is not protection against dishonesty. It is protection against something far more subtle and far more universal: motivated reasoning. The human brain is an extraordinarily powerful pattern recognition machine, and it operates with strong priors. When you have spent 3 years working on an experiment and you have a hypothesis about what the result should show, your brain will, without your conscious awareness or consent, evaluate ambiguous choices differently, depending on whether they push the result toward or away from your expectation. You will find legitimate-sounding reasons to exclude events that pull the number toward the standard model. You will accept systematic corrections that happen to push it toward new physics. You will not be lying. You will genuinely believe you are making the right methodological calls, and you will be wrong in a way that is almost impossible to detect from the inside. Blinding removes the feedback loop. If you cannot see the number, you cannot be influenced by it. Every choice you make about the analysis has to be justified on methodological grounds alone, because you have no idea whether the choice is helping or hurting the significance of the result. It is, in a very real sense, a way of protecting the integrity of the scientific process from the scientists themselves. And the fact that this practice exists, that it is now standard in precision particle physics experiments, says something genuinely interesting about the field's self-awareness regarding the limits of human objectivity. The moment the blind is lifted is, by all accounts, extraordinary. Physicists who have been through it describe it in terms that go beyond the clinical language of scientific results. You have spent years on this. You have debugged code at 2 in the morning. You have argued with colleagues for months about the correct way to handle a particular systematic effect. You have read every relevant paper. You have thought about this measurement in the shower and on airplanes and in the middle of conversations about entirely different things. And then someone types a command or clicks a button and the number appears on the screen. And in that instant, the universe has given you its answer, not humanity's answer, not a committee's answer, the universe's answer, filtered through your equipment and your analysis, irreversible and final. Physicists describe the room in those moments as very quiet, the kind of quiet that has weight to it. The anomalies we have been discussing were real in the sense that they survived this process. The Muon G-2 result from Fermilab was blinded, the analysis was completed, the blind was lifted. The number that appeared was higher than the standard model predicted, and the discrepancy was at a level that the community took seriously. The LHCb Lepton universality measurements went through the same process, multiple times with multiple datasets. Each time the blind was lifted, and the number that came out deviated from what the standard model expected. These were not results that appeared because someone squinted at the data until they saw what they wanted. They appeared because a rigorously controlled, pre-committed analysis procedure produced them. That is not nothing. That is, by any reasonable definition, evidence, not conclusive evidence, not discovery-level evidence, but real, methodologically sound evidence that something in the data was not matching the prediction. The critical distinction, the one that shapes everything that follows, is between evidence at 4 sigma and evidence at 5 sigma. They feel similar when you describe them in words. They are not similar. 4 sigma means you have a compelling anomaly that demands explanation and further investigation. 5 sigma means you have a discovery. The gap between them, in terms of additional data required to close it, can be years of running time on the world's largest machines, and in that gap things can change. The theoretical prediction you are comparing against can shift. The systematic effects you thought you understood can turn out to be slightly different from what you modelled. The fluctuation that was leaning on an accident in the early dataset can reveal itself as a fluctuation when the statistics improve, or the signal can firm up, cross the threshold and become history. You do not always know, going into the data collection, which story you are living. The number at 4 sigma could be a discovery waiting for more statistics, or it could be the high point of a fluctuation that will spend the next 3 years slowly fading back towards zero. From the inside of the experiment in the period between 4 sigma and whatever comes next, both possibilities are equally real. Both are consistent with the data you have. The only thing that distinguishes them is time and more data. And so, the most disciplined thing, the only truly honest thing, you can do is wait. Keep collecting, keep analysing, keep checking your assumptions, and resist the very human temptation to decide what the answer is before the data has told you. That waiting, that suspended state where the answer exists somewhere in the measurements, but has not yet been extracted with sufficient confidence to speak definitively, is where this story was living for several years. And what happened as the experiments continued and the theorists worked harder is not what most people who had been following the headlines were expecting. The story did not resolve in the direction the excitement was pointing. It resolved in a direction that is in some ways more interesting and considerably more humbling. Part 10. The anomalies begin to fade. Let me tell you about a different kind of plot twist. Not the kind where a discovery is confirmed and the textbooks get rewritten and the press conferences happen and everyone involved gets mentioned in the same breath as the names that change physics forever. The kind where the ground shifts beneath the measurement itself, quietly, technically, without drama. Not because the experiment made an error, but because the theory it was being compared against turned out to be less certain than anyone had assumed. This is a harder story to tell because it does not have a villain, and it does not have a hero, and it does not resolve cleanly in either direction. But it is the honest story, and in science, the honest story is the only one worth telling. To understand what happened, you need to understand something about the structure of the Muon G-2, calculation that most of the coverage of the anomaly glossed over entirely. The standard model's prediction for the muon's anomalous magnetic moment is not a single number produced by a single equation. It is a sum of contributions from 3 separate sectors of physics, each calculated by different methods with different levels of precision. The first sector is quantum electrodynamics, the theory of how charged particles interact with light and with each other through the electromagnetic force. QED predictions can be calculated analytically to extraordinary precision, and the agreement between QED calculations and experiment is one of the great triumphs of 20th century physics. The second sector is the weak interaction, the force responsible for radioactive decay, which also contributes a calculable and well understood amount to the Muon's wobble. These two contributions are known so precisely that they are essentially not the source of any meaningful theoretical uncertainty. The third sector is where the trouble lives. The strong interaction, the force that binds quarks together inside protons and neutrons, governed by a theory called quantum chromodynamics, also contributes to the muon's anomalous magnetic moment through a mechanism called hadronic vacuum polarization. Virtual particles involving quarks and gluons pop in and out of the quantum vacuum around the muon and nudge its spin, just as virtual photons and W bosons do. But unlike QED, quantum chromodynamics at the energy scales relevant to the muon's magnetic moment is not analytically tractable. The mathematics becomes what physicists call non-perturbative, meaning the standard technique of expanding the calculation as a series of increasingly small corrections simply does not work. The terms do not get smaller as you go. The series does not converge. You cannot calculate this contribution the way you calculate everything else. So for decades, the hadronic contribution was handled through a workaround. Instead of calculating it directly from quantum chromodynamics, physicists extracted it from experimental measurements of electron-positron collisions, where electrons and positrons annihilate and produce hadronic particles whose properties can be measured and then used to infer the hadronic contribution to the muon's wobble. This technique, refined over many years by multiple experimental groups using data from accelerators in Europe and the United States and Asia, produced a number. That number became the standard model prediction. And that prediction was what the Fermilab measurement was being compared against when the anomaly appeared. The problem, and this is the part that began to unravel the narrative, is that this technique is itself a measurement, not a pure theoretical calculation. It has its own uncertainties, its own systematic effects, its own dependence on the quality of the experimental data used to perform the extraction. And beginning around 2021, and intensifying considerably through 2023 and 2024, a completely independent approach to calculating the hadronic contribution began producing different answers. The technique is called lattice quantum chromodynamics. Rather than extracting the hadronic contribution from experimental data, lattice QCD calculates it directly from the underlying theory of the strong force, by discretizing space-time into a grid and numerically solving the equations of quantum chromodynamics on that grid using enormous computing resources. It is, in principle, a more direct approach, a first principles calculation rather than an experimental inference. And when the lattice QCD results matured sufficiently to be taken seriously, they pointed toward a higher value for the hadronic contribution than the experimental extraction had been giving. A value that, when plugged into the total standard model prediction, moved the predicted muon anomalous magnetic moment closer to what Fermilab actually measured. Let me say that again clearly, because it is the central pivot of the entire story. The muon did not change. The Fermilab measurement did not change. The muon is still wobbling at exactly the rate the experiment recorded. What changed was the number it was being compared against. The theoretical target moved. If the lattice QCD approach is correct, the standard model was always predicting a value closer to the measured one, and the apparent discrepancy, the 4 sigma anomaly that generated years of excited theoretical papers about Z-prime bosons and leptoquarks and dark sectors, was not a window into new physics. It was, at least partially, a consequence of using an imperfect method to calculate a theoretically demanding quantity. At certain moments in the ongoing debate between the two theoretical camps, the experimental extraction approach and the lattice QCD approach, the discrepancy between measurement and prediction appeared to shrink from 4 sigma down to roughly 1 sigma or even less. 1 sigma, in particle physics, is not a signal. It is background noise with a name. This is not a scandal. I want to be very clear about that, because the popular science coverage sometimes implies otherwise. Nobody fabricated data. Nobody made a calculation error that a careful reviewer should have caught. The experimental extraction technique was the best available method for decades, and it produced results that were internally consistent and cross-checked by multiple independent groups. The lattice QCD technique was, for a long time, not mature enough to be competitive. The calculations were too noisy, the systematic effects too poorly controlled to be taken as seriously as the experimental extraction. It took years of methodological development and computational progress before the lattice QCD numbers became precise enough to constitute a genuine challenge to the established prediction. When they did, the theoretical community did exactly what it should. It took the new results seriously, debated them, checked them, and began a process of determining which approach is more reliable. That process is, as of the time of this script, still ongoing. The debate between the experimental extraction and the lattice QCD approaches has not been fully resolved. Both camps have legitimate arguments. Both have identified potential systematic effects in the other's approach. The theoretical uncertainty in the standard model prediction for the muon's anomalous magnetic moment is, at this moment, genuinely unresolved in a way it was not believed to be 5 years ago. What this means for the fifth force narrative is significant. The single most compelling piece of experimental evidence for new physics involving muons. The result that 4 sigma anomaly from Fermilab, the one that launched hundreds of theoretical papers and made it into mainstream news outlets around the world, became ambiguous, not falsified, ambiguous. The signal did not disappear, but the baseline it was measured against became uncertain enough that the significance of the deviation is no longer clear. You cannot claim a 4 sigma discrepancy from the standard model if you're not certain what the standard model predicts. Meanwhile, at LHCb, the evolution of the Lepton universality story followed a different path, but arrived at a similarly sobering place. As the redesigned detector began producing data at its new unprecedented rate, the full software trigger processing its terabyte per second, the improved tracking systems reconstructing particle trajectories with greater precision, the collaboration released updated analyses of the BMES and decay ratios, and as the statistics grew, the numbers moved. The ratio of muon to electron decays, which in the earlier analysis with smaller datasets had appeared to deviate meaningfully from the standard model's prediction of exact equality, began creeping back toward 1. The most significant of these updates, released in late 2022, showed the key Lepton universality measurement sitting comfortably within the standard model's uncertainty range. The 15% deviation that had generated so much excitement, the apparent evidence that the universe was quietly playing favourites between muons and electrons, was gone, not weakened, gone, absorbed into the statistical noise where it had apparently always lived. The emotional texture of watching this unfold from inside the scientific community is worth describing honestly because it is not what you might expect. There was no single catastrophic moment of collapse. No meeting where someone stood up and announced that the fifth force was dead. Instead, there was a gradual cooling. Result by result, update by update, the conversation changed temperature. Papers that had been proposing specific Z-prime models to explain the combined anomalies began to seem less urgent. Conferences that had devoted sessions to the implications of Lepton universality violation began devoting those sessions to other anomalies, other channels, other possible hints. The theoretical ecosystem that had grown up around these specific measurements began quietly to redirect its energy, not in defeat, in the practice pragmatism of a field that has been through this before and knows how to absorb a non-discovery without losing its forward momentum. One commentator, writing about the LHCb result, used a phrase that stuck. The monster dissolved under light. Not dramatically, not with a roar. It simply became less defined as the illumination improved, until at a certain point you could not point to where it had been and say, with any confidence, that there was ever really anything there. What makes this outcome genuinely interesting rather than simply disappointing is the thing it reveals about the process rather than the conclusion. The standard model survived. Again. It has absorbed every serious challenge mounted against it for more than 50 years, and it has emerged each time not by being defended, but by being tested more carefully and found to still be correct. The anomalies were not dismissed. They were taken seriously, which is the only intellectually honest response to unexpected data. They were investigated with the best available tools. They were followed until the data resolved them. And the resolution, when it came, vindicated not just the standard model but the methodology that was applied to testing it. The system worked. That is not a consolation prize. That is the whole point. Whether the final result feels triumphant or unsatisfying depends entirely on what you were hoping to find when you started following this story. If you wanted the fifth force to be real, this chapter stings. If you wanted to see science operate the way it is supposed to, rigorously, honestly, without attachment to preferred outcomes, then this chapter is exactly the demonstration you were looking for. The standard model is still standing, battered slightly by the scrutiny, tested more carefully than it has been in years, and standing. But standing is not the same as finished, and the questions that the anomalies raised about what lies beyond the 5% of the universe we can see, about whether the Muon is pointing at something we have not yet found the right instrument to measure, those questions did not dissolve when the signal did. They are still there, waiting for the next experiment, the next dataset, the next number in the 8th decimal place that refuses to behave. Part 11. What if we almost saw it? The fading of an anomaly is not the same as a refutation. This distinction sounds like the kind of thing a scientist says to soften a disappointment, to preserve some dignity after a result fails to pan out the way everyone hoped. But it is not rhetorical comfort. It is a precise and important epistemological point that governs how science actually advances at its outer edges, and understanding it changes how you read the entire story of the fifth force anomalies. When a signal weakens as data improves, the situation is genuinely ambiguous in a way that resists the clean narrative of either triumph or failure. There are 3 interpretations available, and the honest position is to hold all 3 simultaneously, rather than defaulting to whichever one feels most comfortable or most dramatic. The first interpretation is the one most comfortable for defenders of the standard model, and also the one that requires the least imagination. The anomalies were statistical fluctuations. Early datasets with limited statistics occasionally produce apparent deviations from the expected distribution purely by chance. This is not a flaw in the experimental methodology. It is not a failure of the analysis teams. It is built into the fundamental mathematics of random sampling, and it happens with a predictable frequency that the sigma system is specifically designed to account for. If you flip a perfectly fair coin 100 times, you might get 60 heads. That is a 10% deviation from the expected 50%. It looks significant. It feels significant, especially if you were expecting to see a biased coin. But flip it 10,000 times, and the ratio stabilizes near 50%, and the apparent bias dissolves back into the noise where it always lived. The LHCb Lepton universality result in this interpretation was the physics equivalent of 60 heads in 100 flips. It looked like the universe was playing favourites between muons and electrons. It was not. It was the ordinary, mathematically guaranteed misbehaviour of small samples, doing exactly what small samples always do when you're not yet watching carefully enough. This interpretation is supported by the trajectory of the data. The Lepton universality result moved toward the standard model as the dataset grew. That is the expected behaviour of a statistical fluctuation. It regresses toward the true value as the statistics improve, because the true value is what the standard model predicts. The Muon G-2 situation is more complicated, for reasons involving the theory rather than the experiment, but the overall pattern is consistent with a community that got excited about early hints that did not survive the scrutiny of better data. The 5 sigma rule exists precisely to prevent this kind of premature conclusion. The anomalies never reached 5 sigma. They were always in the zone of things that require more data rather than things that can be announced, and more data eventually is what arrived. The second interpretation is more interesting and considerably harder to dismiss, which is why it deserves more than a quick mention before moving on. The effect may be real but smaller than the initial data made it appear. The true deviation from the standard model may genuinely exist, embedded in the physics, but at a level that the early dataset's statistical uncertainty inflated into something that looked much larger than it actually is. In this scenario, the signal is not a fluctuation that goes to zero with more data. It is a genuine feature of physical reality that goes to its true, smaller value with more data, and that true value, while not as dramatic as the early hints suggested, is still non-zero. This interpretation cannot be ruled out. The updated LHCb results did not measure Lepton universality to be exactly 1, exactly the standard model value, with 0 uncertainty. They measured it to be consistent with 1 within the current uncertainties. Those uncertainties are smaller than they were before, but they are not zero. There is still room, within the error bars, for a small but real deviation. The revised Muon G-2 comparison is similarly ambiguous. The lattice QCD predictions have moved the theoretical value closer to the measured one, but the two theoretical camps, the experimental extraction approach and the lattice QCD approach, have not yet agreed on a single number, which means the true theoretical uncertainty is larger than either camp alone would suggest. In that expanded uncertainty, there is room for the anomaly to still be real, just smaller than it appeared. A small signal, if real, is still a signal. This is worth saying clearly, because there is a tendency in popular science coverage to treat the anomaly shrank as equivalent to the anomaly vanished. These are not the same thing. If the true deviation from Lepton universality is 5% rather than 15%, that is still a violation of a fundamental symmetry of the standard model. It is still evidence of physics beyond our current framework. It still requires explanation. The fact that a 5% deviation is harder to confirm than a 15% deviation, that it requires more data, more careful analysis, more time, does not make it less real if it is there. It just makes it more demanding of patience and precision. And particle physics, whatever its other limitations, has never been short of patience or precision. The third interpretation is the one that sits differently from the other two, the one that, if you follow it carefully, changes the shape of the entire story. The anomalies may have been pointing at something real, but something different from what the simplest versions of the fifth force theory predicted. Consider how the history of physics actually unfolds. The right theory is almost never the first theory proposed to explain an anomaly. When the orbits of Uranus did not match the predictions of Newtonian gravity, the first proposals involved all kinds of mechanisms that turned out to be wrong. The correct explanation, an eighth planet, Neptune, was found only after the incorrect explanations had been systematically eliminated. When the photoelectric effect defied classical electromagnetism, the first theoretical attempts to explain it within the existing framework failed, before Einstein proposed the photon and rewrote the rules entirely. The history of science is not a history of correct first guesses. It is a history of wrong theories pointing, however imperfectly, at real phenomena that required better theories to describe. The models proposed to explain the Muon G-2 anomaly and the LHCb lepton universality violation simultaneously. Specific Z' bosons with specific coupling structures, specific leptoquark models with specific mass ranges and interaction strengths. Those specific models may be wrong. The anomalies did not firm up into the exact signatures those models predicted. But the question of whether the underlying phenomenon those models were attempting to describe is real or not is a separate question. There may be something genuinely new at the energy scales these experiments were probing, something connected to dark matter, something extending the standard model in a direction we have not correctly mapped yet, that does not produce exactly the signatures the theorists drew up in the years between the anomaly's appearance and its fading. The models were attempts to identify the territory from a very early and incomplete map. The territory itself may not have moved. The broader context in which this entire story sits is also worth holding in view, because it is easy to lose sight of it when you are focused on the specific trajectory of two specific anomalies. The standard model, for all its extraordinary predictive power, is known with certainty to be incomplete. It does not describe gravity, the most familiar force in everyday experience, the one that holds you to the ground and keeps the planets in their orbits, has no place in the standard model's mathematical framework. The attempts to reconcile quantum mechanics with general relativity, to build a theory of quantum gravity, have occupied some of the best mathematical minds of the past century, without producing a confirmed theory. The standard model also does not explain why the universe contains more matter than antimatter, why the Big Bang produced a slight excess of particles over antiparticles, why that excess survived the mutual annihilation of matter and antimatter in the early universe, why anything exists at all rather than nothing. It does not account for dark matter or dark energy, which together constitute roughly 95% of the universe's total energy content, and it contains approximately 19 free parameters. Numbers, like the masses of the quarks and leptons and the strengths of the three forces it describes, that are not derived from any deeper principle. They are simply measured experimentally and inserted into the equations by hand. A truly complete theory of reality would explain why those numbers have the values they do. The standard model treats them as inputs, not outputs. It is a framework of extraordinary precision and extraordinary incompleteness, simultaneously. The anomalies in this context were not random events. They emerge from experiments specifically designed to probe the edges of the standard model's validity, to look at quantities where new physics, if it exists at a mass scale not yet directly accessible, would leave its most detectable fingerprints. The strategy was correct. The methodology was sound. The anomalies that appeared were real in the sense that they survived rigorous analysis. The question of whether they represented the thing everyone hoped they represented, a genuine crack in the framework, a first signal from beyond the standard model, remains genuinely open. They may have been the first hints of the physics that fills the standard model's known gaps, or they may have been noise that happened to appear in interesting places at an interesting time. We do not know yet, and the honest acknowledgement of that uncertainty is not a failure of the investigation. It is the investigation operating correctly. The history of false positives in particle physics deserves a mention here, not to be discouraging but to calibrate expectations honestly. The Dharma experiment, located in a laboratory deep under Gran Sasso Mountain in Italy, has claimed for decades to detect dark matter through an annual modulation in its signal rate, a seasonal variation that matches the expected change in dark matter flux, as the Earth's orbit brings it alternately toward and away from the direction of the dark matter wind produced by the solar system's motion through the galaxy. The signal is real in the sense that the modulation is genuinely present in the data, but no other experiment, using different detection technologies and located in different parts of the world, has confirmed it. The ATLAS and CMS experiments at CERN saw a tantalizing excess of photon pairs at an energy of around 750 giga-electron volts in data, collected during 2015 and 2016. The excess generated extraordinary excitement. In the months following its announcement, hundreds of theoretical papers were written, proposing explanations, new particles, extensions of the standard model that could account for it. And then the 2016 dataset arrived with more statistics, and the excess was gone. Completely gone. Not weakened, gone. It had been a statistical fluctuation of almost precisely the kind that the mathematics of small samples predicts will occasionally occur. These are not cases of bad science. They are not embarrassments that the field should be ashamed of. They are demonstrations of the statistical universe behaving in exactly the way the mathematics says it should behave. Random fluctuations occur. They occur less frequently at higher sigma levels, but they occur. The lesson is not that we should be less excited by anomalies, or more cynical about unexpected results. The lesson is that excitement should be carefully calibrated to the sigma level, to the track record of similar signals at similar significance thresholds, to the question of whether independent experiments are seeing the same thing through different methodologies. Calibrated excitement is not diminished excitement. It is excitement that survives contact with more data. Physics at the edge of knowledge is an experience of living with unresolved tension that does not resolve on a human timeline. The universe does not owe us clean answers by the end of the fiscal year. The anomalies appeared. They were taken seriously, which was the right response. They were investigated with extraordinary care and resources, which was also the right response. They weakened. But they have not fully vanished, and the questions they raised have not been fully answered. We have not found the fifth force. We have also not proven it does not exist. Those are not the same statement. And in the space between them, in the gap between absence of proof and proof of absence, the real work continues. The Muon G-2 theoretical debate is unresolved. The LHCb datasets are still growing. The Run-3 data from the upgraded collider is still being analysed. The lattice QCD calculations are still being refined and cross-checked against the experimental extraction approach. New experiments targeting the muon's properties are in development. The story has not ended. It has entered a phase of slower, more careful, more demanding investigation. The phase that comes after the initial excitement, when the easy answers have been ruled out and what remains requires more precision, more time, and more intellectual honesty about what is and is not yet known. What this means for the fifth force hypothesis is not death. It is dormancy. The evidence that seemed most promising has quieted. but the theoretical framework, the mathematical possibility of a force that couples selectively to specific particles, that bridges the visible sector of ordinary matter and the dark sector that constitutes the hidden majority of the cosmos, that leaves the atoms of your body completely unaware of its passage while influencing the quantum behavior of a muon in a magnetic ring. That framework is still standing, still mathematically consistent, still viable, still under the right experimental conditions, detectable in principle. The question is simply whether those conditions are within reach of the experiments currently running, or whether they require something we have not yet built. And that question, unlike the anomalies themselves, shows no sign of fading. Part 12. The Minority. We come, finally, to the place this entire story has been building toward. Not conclusion, because there is no conclusion, but landing. A place where the threads come together not into an answer, but into a clearer view of the question. And I want to take my time here, because the view from this particular place is worth looking at carefully. It is not the view you get from a triumphant discovery. It is something quieter and, I would argue, more honest. It is the view you get when you have followed something as far as the current evidence allows and arrived at the edge of what can be known with what we currently have. That edge is not a wall, it is a shoreline, and standing at a shoreline tells you things that standing in the middle of the land cannot. You are at this moment made of roughly 10 to the power of 28 atoms. That number is so large it barely registers as a number. It is more like a statement about the relationship between the scale of human experience and the scale of the physical world. 10 to the power of 28. If you counted one atom per second without stopping, it would take you longer than the current age of the universe to finish. Each of those atoms consists of a nucleus surrounded by a cloud of electrons, and the nucleus is made of protons and neutrons, and the protons and neutrons are made of quarks bound together by the strong nuclear force. Every single one of those quarks, every single one of those electrons, interacts with the four fundamental forces we know. The strong force holds the nucleus together. The electromagnetic force governs the chemistry of your cells, the electrical signals in your neurons, the light entering your eyes. The weak force governs certain radioactive decays that are essential to the nuclear processes in the sun that ultimately power most life on Earth. Gravity keeps you on the planet. 4 forces. Everything you have ever experienced, everything you have ever touched or seen or measured, every instrument ever built by human hands, all of it runs on those 4 forces and their interactions with the particles of the Standard Model. And the Standard Model accounts for approximately 5% of the universe. That sentence is worth sitting with for longer than it takes to read it. Not because it is new information, we have mentioned the numbers before in this story, but because of what it means from the inside of the situation. You're not just a small thing in a large universe. The way a person is small compared to a planet or a planet is small compared to a galaxy. You are a 5% thing in a 95% universe. The forces that built you, the forces that sustain every process in your body right now, the forces that connect you to every other thing you have ever interacted with. They are the minority physics. They are the exception. They are the edge case. The vast majority of what exists operates apparently by different rules, through different mechanisms, producing different structures in a way that your atoms are fundamentally not equipped to register. You're not just ignorant of the other 95% in the way that you might be ignorant of events happening on the other side of the planet. You're structurally excluded from it. Built from the wrong stuff to participate in whatever is happening over there. The Muon anomaly, the boson decay measurements, the years of careful analysis at Fermilab and at LHCe, all of that was an attempt, launched from inside the 5%, to reach across and touch the other 95. Not with our hands, not with any instrument built from ordinary matter in any ordinary way, but through the most delicate possible indirect means. Watching how a muon wobbles in a magnetic field, counting how often a quark decays one way versus another, looking for the fingerprint of something invisible in the behavior of something we can see. And for a brief, exciting, genuinely uncertain period of several years, the data looked like it might be showing us something real. Like the boundary was thin enough, in those specific measurements, that something from the other side was pressing against it hard enough to leave a mark. The cosmic radio analogy comes back here with more force than when we first introduced it. We have 4 channels, 4 forces, and they are the only ones we can hear. Every piece of information we have ever gathered about physical reality has come through those 4 channels. Every particle detector, every telescope, every gravitational wave observatory, every cosmic ray experiment, every measurement ever made in every laboratory in the history of human science, all of it is receiving signals on those 4 frequencies and nothing else. The other channels, if they exist, have been broadcasting through us for the entire history of the universe. Every second of your life, everything that has happened to you, every room you have ever been in, every landscape you have ever seen, all of it has been permeated by transmissions you are constitutionally incapable of receiving. Not because the signal was weak, because you are not the right kind of receiver. Your atoms simply do not have the quantum properties required to interact with whatever is being transmitted on those other channels. The only reason we even know to suspect those other channels exist is gravity, because dark matter has mass, and mass warps space-time, and the warping of space-time is something our instruments can detect even when the thing producing the warping cannot be seen in any other way. Galaxies rotate at speeds that only make sense if there is vastly more mass present than we can account for with visible matter. Clusters of galaxies bend light from more distant objects by amounts that require invisible mass. The large-scale structure of the universe, the way galaxies are distributed in filaments and sheets and voids across cosmological distances, matches simulations that include dark matter and fails to match simulations that do not. Gravity told us. It is the one force that both sectors share, the one thread connecting the visible minority to the invisible majority, and without it we would have no evidence at all that the other 95% exists. We would be standing in our 5% world, completely unaware that most of reality was not us. Return now to the anomalies, with all of that context in place. The muon wobbling slightly faster than expected in the Fermilab magnetic ring. The B mesons decaying with a slight preference for electrons over muons at the LHCb detector. If the fifth force interpretation was correct, if those deviations were real and caused by a new boson coupling preferentially to muons and to dark matter, then those measurements were something genuinely extraordinary in the history of human knowledge. They would have been the first moment where the barrier between the 5% and the 95% was thin enough, in a specific and controllable experimental context, that we could feel something pressing through from the other side. The muon, that brief and inconvenient particle that nobody asked for, and that seems to serve no essential purpose in the architecture of ordinary matter, would have turned out to be a kind of antenna, a particle that belongs to our world but is tuned, just slightly, to a frequency we cannot normally hear, a bridge particle, the first crack in the wall between what we are made of and what most of the cosmos is made of, and then the calculations shifted, and the data improved, and the signal softened, and the universe, with the infinite patience of something that has been operating for 13.8 billion years and does not particularly care whether we understand it or not, declined to confirm what we thought we saw. The theoretical prediction moved toward the measurement, shrinking the discrepancy. The larger LHCb dataset moved toward the standard model prediction, dissolving the apparent asymmetry. The moment of almost knowing retreated. The boundary, which had seemed briefly permeable, reasserted itself. This is the version of the story that does not fit comfortably into a headline. The headline said things like, CERN discovers possible fifth force, and Fermilab hints at revolutionary new physics. Those headlines were not dishonest. They reflected the state of the evidence at the time they were written. But the actual story, the full story followed from beginning to wherever we currently are, is more complicated and in its own way more interesting. Scientists built the most sensitive instruments in human history. They pointed those instruments at the fabric of reality with more precision than had ever previously been achieved. They found a whisper. They spent years, carefully, rigorously, with extraordinary methodological discipline, trying to determine whether the whisper was language or static, whether it was signal or noise, whether the universe was telling them something or whether they were hearing their own hopes reflected back at them from the data. And at the end of all that work, they are still not entirely certain. The whisper has gotten quieter, considerably quieter, but it has not fully gone away, and the theoretical situation remains unresolved enough that certainty in either direction would be premature. The philosophical question at the centre of this entire investigation, how do you prove the existence of something that cannot interact with you, does not have a satisfying answer in the conventional sense. It sits at the genuine edge of what the scientific method can do, Not because the method is flawed, but because the question itself is structurally hard in a way that goes beyond any particular experiment or analysis technique. If a force passes through you without leaving any trace in your atoms, without nudging a single electron, without influencing a single chemical reaction, you cannot detect it. That is not a technology problem, it is a physics problem. The only pathway to detection is if the force also interacts, however faintly, with something that you can detect. Something that has the right quantum properties to feel its influence. The muon was that something, potentially. The fifth force hypothesis was a specific and testable proposal for how that faint interaction might be occurring. The evidence has so far not been strong enough to confirm it, but the strategy, using particles with exotic quantum properties as probes of forces that ordinary matter cannot feel, remains the right strategy. It is the only strategy available to 5% creatures trying to detect 95% physics. There is something worth pausing on here. Something that gets lost in the disappointment of a non-discovery. The fact that this investigation was possible at all, the fact that we could build machines sensitive enough to measure the muon's wobble to 8 decimal places, that we could reconstruct the decay products of a particle living for a trillionth of a second, that we could perform theoretical calculations of sufficient precision that a discrepancy in the 8th decimal place could even be identified as a discrepancy, that is itself an achievement of staggering proportions. The question was not just asked. It was asked with enough precision to actually get a meaningful answer, even if the answer was not yet confirmed. And meaningful answers, even negative ones, change the map. Consider the Michelson-Morley experiment of 1887. Albert Michelson and Edward Morley set out to measure the speed of light through the luminiferous ether, the invisible medium that physicists of the time believed must permeate all of space, serving as the substance through which light waves propagated, the way sound waves propagate through air. The experiment was extraordinarily precise for its time, using an interferometer capable of detecting the tiny difference in light travel time that the ether wind would produce as the Earth moved through it, and it found nothing. The speed of light was the same in every direction, regardless of the Earth's motion. The ether did not appear to exist. The result confused and troubled the physics community for years, because it contradicted a deeply held assumption about how reality worked, and nobody immediately knew what to do with it. But that null result, that precise, careful measurement of something that was not there, was the experimental foundation on which Einstein built the special theory of relativity 18 years later. The absence of the ether, measured precisely, was the clue that space and time were not what anyone had thought they were. The negative result was, in retrospect, the most important result in physics of that era. Not a consolation prize, the actual discovery. We may be living through something analogous. The fifth force anomalies may not have been what they appeared to be. The specific models proposed to explain them, the specific Z-prime bosons with specific coupling strengths, the specific leptoquarks with specific mass ranges, may be wrong. But the precise manner of the anomaly's appearance and subsequent fading has told us things we did not know before. It has told us that muons are uniquely sensitive probes of physics beyond the standard model, more sensitive, gram for gram and measurement for measurement, than almost any other particle we can practically work with. It has told us that the theoretical calculation of the hadronic vacuum polarization contribution to the muon's magnetic moment was less well understood than anyone realized, and that resolving the tension between the experimental extraction approach and the lattice QCD approach is now one of the most important open problems in theoretical particle physics. It has told us that LHCb, with its new capabilities, is going to be producing Lepton universality measurements of unprecedented statistical power for years to come, and that any genuine violation of Lepton universality at even the few % level will eventually be impossible to hide from it. And it has told us, with more precision than we had before, exactly where the boundary of the standard model's confirmed validity currently lies. That boundary is real, and it has a location. Finding its location is progress, even when the location turns out to be slightly further away than you hoped. You exist right now, inside a universe that is mostly hidden from you. Not metaphorically, physically. Roughly 27% of what exists is dark matter, mass that has gravity but no electromagnetic interaction, invisible to every optical and radio telescope ever built, undetected by every direct detection experiment ever run. Another 68% is dark energy, an even more poorly characterized phenomenon associated with the accelerating expansion of space, about which we know essentially nothing beyond its gravitational effects on the large-scale structure of the cosmos. 5% is ordinary matter, the quarks and electrons and photons and everything built from them, including you, including every star and planet and galaxy you have ever observed. 5%. You are in the extreme minority of physical reality, and you have been your entire life, and so has every human who ever lived, and so will every human who comes after. The universe is not mostly made of stuff like you. It is mostly made of stuff nothing like you. And it has been that way since the beginning. The anomalies that this story has followed, the muon's wobble, the quark's decay preferences, the years of measurement and analysis and theoretical debate, were attempts by 5% creatures to hear a transmission from the other 95. The instruments were real. The methodology was sound. The anomalies were genuine in the sense that they survived rigorous analysis before weakening under better data. Whether they were the first faint static from another channel of reality, or the last gasp of a statistical fluctuation, that question is not yet fully resolved. The universe has declined so far to say definitively which. And there is something almost appropriate about that. Not comforting, appropriate. Because the universe has never owed us clarity on our timeline, it operates according to its own rules, at its own pace, indifferent to our need for resolution. We are the ones who built the machines. We are the ones who chose the questions. We are the ones waiting for the answers. The universe is just doing what it has always done, existing in all its inaccessible 95% complexity, while we press our instruments against its surface and listen as carefully as we can. How do you prove the existence of something you cannot interact with? You build the best machines you possibly can. You measure what you can measure with the greatest precision available to you. You look for the anomalies, the edges, the whispers in the data, where the boundary between the known and the unknown is thinnest. You take those whispers seriously, because dismissing unexpected data is how you guarantee you will never find anything genuinely new. You investigate rigorously and honestly. You follow the evidence wherever it leads, including when it leads you back toward the standard model rather than away from it. You update your understanding when the data changes, and then you build better machines and you look again, because the question has not gone away just because the current answer is inconclusive. That is not a failure mode. That is the only mode available to beings built from 5% of the universe trying to understand the rest of it. The fifth force may exist. It may not. The anomalies may have been the first faint fingerprints of something real that we have not yet learned to read correctly. Or they may have been noise wearing the costume of signal, the way noise sometimes does when you're looking hard enough and hoping hard enough and the statistics are just barely on the wrong side of the threshold. We do not know. And the willingness to sit with that not knowing, to keep working, keep measuring, keep refining, without forcing a premature conclusion in either direction, that is not weakness. That is the discipline that makes eventual discovery possible. Somewhere in the 95% you cannot reach, there may be a signal, a force, a bridge, something that has been passing through your body every second of your life, that passed through every human who ever lived, that is moving through the walls of the room you're in right now and through the rock beneath your feet and through the space between the galaxies, leaving no trace in anything we have ever built to detect it. The anomalies pointed at it, briefly, or they pointed at nothing. The instruments are still running, the data is still accumulating, the calculations are still being refined. And the question, that particular question, the one about what is on the other side of the boundary we are built from, that question is still open. The openness of the question is the real discovery. Not a particle, not a force, not a confirmed signal from the dark sector, but the precise and honest acknowledgement that most of what exists lies beyond the reach of what we are, combined with the absolute refusal to stop looking anyway. That is what this story is actually about. Understanding the exact dimensions of your ignorance is perhaps the most important thing you can know, because it tells you exactly where to point the next instrument, exactly where to look when the better machines are built, exactly where the universe has been most carefully keeping its secrets. The signal is still out there, or it is not. We are still listening, and we will not stop.